Okay, here we go. Continuity. Basically, it comes from the word continuous. Our basically very slim definition of this is that a function whose graph can be sketched without lifting the pencil. A lot of them that we've done recently with holes or asymptotes, obviously, you can't do those without lifting your pencil. And so those are not continuous. And basically, to tell the difference, you look for discontinuities. If it has a hole or an asymptote, there's no shot that it's continuous. So now, this is a much more strict definition here. Continuity at a point. They're going to say an interior point, because the reason they say that is I'm going to give you some interval. I might say negative infinity to infinity. I might say from 4 to 7. So if I say something like 4 to 7, right, an interior point would be like 5. You agree with that? Or 6, or 5.5. That would be an interior point. Do you understand that? So they're saying that an interior point, basically it'll be continuous if, well, as long as it's in the domain, which obviously that's the x values, if basically the limit exists and it is equal to whatever you get by substituting it in. Okay? And basically what that's saying is if substitution works. Right? So if substitution works, then it is continuous. And let's face it, if you had a graph like this, is it okay to just get the y value, and isn't that the limit? If there's no holes? Okay. Well, what if there happens to be a problem, and there's a hole, and can you still find that limit? Well, you can, but they're saying for continuity, that's not continuous, because you would actually have to lift your pencil up and hop over that hole. Okay. And in other words, that's not just the y value. Maybe it's actually up there. Okay. This will be more clear when we do a couple. This is the one that's kind of tricky. What are the endpoints of the example that I've given you up there? 4 and 7, right? Isn't that kind of hard? So it'd be like looking here and looking there, right? What they're saying is we'll consider it continuous as long as I can come, if it's the left endpoint, as long as I can come in from the right, and if it's the right endpoint, as long as I can come in from the left, then you're okay, is really what it's saying. And that's what this is saying in lots of words and symbols. Okay? But they're saying the limit as a from the right for f of a, that's really this one over here on the left, and from the left for f of b, that's the one on the right. Lots of big symbols and limits and all that good stuff. You might want to get used to starting to read some of that on your own, because there's no guarantee what you're going to get at the next level. You might have to decipher that and translate that. And as you can tell, I brought it from Word, and it didn't like that very much. All right? Not that hard. Let's take a look. I tried to break this one down for you. Notice I didn't even make you do the piecewise this time. I just gave it to you. So now the first question is, does f of 0 exist? Now here's the problem. Have I given you f of x? Have I told you what that function is? I've just given you the graph. So f of 0 existing means I'd like to plug 0 into some function I don't even know. But if you plug 0 into a function, what do you normally get out as a result? You get a number, right? And normally it's the y value, right? So they're going to say, does that exist? So you look at 0 for an x value. Do you agree that's pretty much, ooh, better not use blue. Anywhere along that y-axis, that's where x is 0, right? Is there actually a point on here that if I got all the ordered pairs and listed them all down, would one of them have 0 comma something? Where is that point? 0 comma? Do you agree it's right there? So does that exist? Is it there? Okay, so yes, it does. And if you really want to know what it is, it's 1, right? If people ask you, because I could write it as 0 comma 1. That's actually a point. See the 0 goes right there. Do you see that? And once again, we're kind of looking at y values here, the output. So how about, does the limit as x approaches 0 from the right, does that exist? Again, x value of 0 is actually right in here, correct? So you got to go to the right of that anywhere you want. So we're going to go right there. We're going to hop on the road. And as I get closer and closer to 0 as an x value, is there something there? Yes, there is. And in this case, well, what does that happen to be? Happens to be 1. Okay. So does f of 0 equal the limit as it approaches from the right? Yeah, because it is really, in this case, this answer is letter A, right? It's 1 equals, this is letter B, is 1. So do they equal? Yes, they do. So is it continuous at that point? Yes, because they're the same thing. Do you see? That's really what this is saying. Are they the same thing? That's all it's saying. In a really weird fashion, but that's all it's saying. So I picked a point, I said 0. Is it there? Is there a y value? Yes, it is. Okay. Is the limit the same thing? Yes, it is. They're the same. So is there a limit? Yes, there is. It's 1. Are they the same thing? Yes, it is. So is it continuous? Yes. Do you agree that I could graph this portion with no problem? Is it continuous right there? Yeah. Is this graph continuous everywhere? No. Okay. Obviously, because I wouldn't be able to do this whole thing without lifting my pencil. Okay. So questions on that first one, basically you look for what is the actual y value there. Is the limit the same thing? If it is, good. If it's not, bad. That's about it. Let's try another one. F of 2, does it exist? Let's go find out. So I'm putting 2 in for what? For x or for y? For x, right? So it's 2 comma something is what I'm looking for. And in this case, if I go here, does it exist? Yes, it does. What is it? Very good. I want to see who said 1, but nobody did. You're actually looking for the dot. You agree? Do you agree that 2 comma 1 is not actually a dot on this graph? But is 2 comma 2 a dot on this graph? Yes, it is. Okay. So how about this one? Does the limit as x approaches 2, notice I didn't do right and left here, does that exist? Now, so you got to check both though, right? So get on from the left. It goes to that value. Agreed? If you get on to the right, it goes to that value. So are they going to the same value? So does the limit exist? Yes, it does. And what is it? 1. So, yes. Yep.
You can use either. At x equaling 2, you can use either point. You know what I mean?
No, I don't.
It's like the first one's at 2.
Right. This is basically asking what is the actual y value. That's what that is asking.
Which would be the colored in dot.
Yes.
Which is x2.
Exactly. This as an x, we're looking for the x value. This is saying what does the y value get closer and closer to as I move along the road.
And you can't use the dot point.
That's right. Exactly. There's no road to get there. That's off on an island somewhere. You'd have to take a boat. So f of 2 is 2. Does that equal 1? No. So is it continuous there? Do you agree with that? Do you agree that if I tried to do this by hand, I would actually have to just pick up my pencil and then move over to the next spot? Because obviously some people say, well, you can go around in a circle and then shoot out the other way. Yeah, but remember, that's not actually there. We make that huge so you can see it. If you graph that on a TI-83, there'd be just the smallest little dot in the world. You could zoom in 10 times and you'd maybe barely be able to see it. Okay? So yeah, it is not continuous there. So what do you think? Is f of x continuous at x equals 4? What do you think? If you just had to look at the graph and you didn't have to do all that work, what do you think? At x equals 4. Right, but it's an endpoint. So if it's an endpoint, you only have to come in from the... You only have to come in from one direction if it's an endpoint. So you'd be doing this one. I have to come in from the left. And can I... Whoa, did I go too far? Oh, no, here. Can I do that? Yeah. So really what you would be checking is what is f of 4, and what is it? 1. And you would be checking what is the limit as x approaches 4 from the left, because it's an endpoint. And can you do that? Yeah, if you get on 4 from the left, and what are we getting closer and closer to? 1. Are they the same number? So it's continuous. Okay. This is why this is a much stricter definition. This is truly the mathematical definition of continuity. Okay. Hey, could we say it this way before? No, because we've never done limits. So we couldn't say it this way before. How about 1? What do you think? X equal 1? You think it's continuous? Now where does that fall in? Is it like this? I'm asking from 4 to 7. Here I'm really asking from 0 to 4, right? Is this an interior point we're talking about or an endpoint? Interior point. I'm talking from here to here. That's where I have graphed. That is inside those two lines. That's where I've graphed. Okay? So what is f of 1? Very good. Who said that? I thought for sure somebody'd say 0. F of 1 is 1. How about the limit as x approaches 1? And we have to do both ways because it's an interior point. Well, this one goes to 0. That one goes to... So what are you supposed to answer then? Yeah, it doesn't matter. Are those the same? No. So is it continuous there? No. Let's say, can you look at that graph and tell it's not continuous? Yeah, but I'm making you do the definition here. Okay. If a function is not continuous, the one we just had is definitely not continuous, then it must have some type of discontinuity. Do you agree with that statement? Okay. There are a lot of different types of discontinuities. Graphs A and B right here. Do you agree that there is a discontinuity in both of them? Well, I think we kind of know what that's called. Whole or removable. Basically, I like to use removable because basically, do you agree if I fill in that dot, I have removed the problem? Okay, that's pretty easy to remove that one. Or it's a hole. I wouldn't be too upset if you called it a hole. But it is actually a removable discontinuity. Okay. Because remember, when do you get holes again? Algebraically? When factors cross off, right? So did you just basically remove them? You did. What's next? Just graph C here has, and we just had one of these in the last example, didn't we? It was going along just fine, and then all of a sudden went somewhere else. This is a jump discontinuity. No fair looking in the book. You might have a good guess without looking in the book as to the answer for this next one, because the two graphs are going out to, ooh, non-removable is good, not what I was looking for. But non-removable would also be a, because those over there are really non-removable as well, the jump discontinuities. But I like how you said non-removable, that's good. They are infinite or asymptotic. You could use that word if you want, but infinite's just shorter. Yeah. All right. You can get a graphing calculator if you want, but I have it up here if you don't want to go get it. This particular one, yeah, and you can just, I actually have the same range as you do, but I actually took it off the TI-83. This is -1. That is +1, +1, -1. It basically comes on in and then just freaks out. And then it stops going like that. Okay, that's what the graph does. Can you follow that path to do limits and stuff? Can you follow when things are going all over the place? No. And so what is that graph really doing? Okay, it's actually, they actually make some fans this way. Oscillate. In fact, that one is one. Oscillating means going back and forth. Okay. Other places on this graph are fine. It actually just smooths right out, as if nothing ever happened. Okay. But in the middle, it just goes crazy. Yeah, I'd say go in and just go crazy and then go out the other side. I don't think you have to go and get points in the table. I think we're good. But make it obvious what it means by oscillating, you know, when you do it. I hope that's not an EKG. That would be. You would go from dead to going really fast to, once again, dead. In the span of perhaps 2 seconds, if that was seconds on the bottom. Yeah. Okay. Determine all point or points of discontinuity. Notice, if you graph both of these individually, they would be what? Parabolas, cubics, what would they be? Lines, right? So I kept this pretty simple, right? 3x minus 2 is a y-intercept of -2 and a slope of 3, correct? So I bet you if I hit the y-intercept of -2, this will probably graph, seeing it's supposed to go all the way to 0. And there it is. And at 0, -2, should I have a filled-in circle or open? I kind of left that there for you to decide. What was it? Filled in. Yep, very good. And I think this other one I did for you, but it's going to be what? The initial dot? Well, let's find out. Do you agree that the y-intercept here is 3 and a slope of -1/2, right? Okay. And so there it is. Do you agree with the open? Okay. So I chose a pretty simple piecewise here just to show you. So it says determine all point or points of discontinuity. So what I'm looking for are x values. Well, the first thing we should probably talk about before we do anything is talk about, oh, maybe this is why we've been working on this so hard. Well, I better not put anything. Give you a chance to graph your lines there. Domain. To, yes, infinity to infinity. There is one possible questionable point, though, correct? And that is 0 might be questionable, but it's good, right? And those lines obviously are infinite. They're going to keep going. How about range? Very good. Negative infinity to 3, not including 3. And it was said the way I wanted to. Very good. In fact, a lot of those y values are going to happen twice. Okay. All right. So the first thing you should always look for when looking for discontinuities, especially if you're not given an interval, is to look for anything that's not in the domain. But do you agree that pretty much everything's in this domain? Yeah, I mean, obviously if I didn't have the blue graph on here, so let's say that's not even on there, obviously isn't -4 a discontinuity then, because there's nothing over there? All right, so you would list that as well. But our domain is covered. We got it all. So are there any discontinuities here? There is a discontinuity, right? And what x value is there a discontinuity? 0. So you would say there is a discontinuity at x equals 0. And what type is it? What are our options? Our options are, let me review them with you, removable, jump, infinite, or oscillating. Jump, yep. Because that's the x value at which the jump occurs. Do you agree that at x, that's where it jumps? Yep. Yeah, it was traveling along just fine here on this blue line, and all of a sudden, whoa, way out up on the red line. So that's where the jump actually happened. Okay. Oh, there you go. There's a nice graph for you. Oh, sorry. Yes. Yeah, you can. There can definitely be more than one in a graph. Yeah. Mm-hmm. Yeah. Oh, you mean like if it was connected? Oh, 'cause I kind of thought you were talking about that, or something, you know. Something. Oh, just a complete line with a hole in it. Don't think that would ever happen, but yeah, that would possibly be true. Mm-hmm. Yep. Yeah, it would be a jump and a removable at that point. Yeah. Mm-hmm. Yep. I didn't understand the question at first, but now I got it. All right. So here we go. Well, we better talk about. We'll give you a second to do that. That is on there, right? Okay, good. Domain, please. Including both? Are you sure they're all in there? Okay. And range? -2 to Okay, so I got a tricky range on you there just to see what you would do. It's -5 to 4 for the domain. I agree with that. The range is -2 to 4, all of which are included, and then 5. But not in between 5. I don't have 4.5. I don't have 4.25. I don't have 4.75. All right. So -2 to 4 with, and also 5. So now, what's different between our basically the domain is what you're looking at. What's different from this domain and the last domain? Yeah, last domain had all sorts of stuff in it. This domain does not, and I wrote it in the wrong spot. And I don't think it's going to let me move it, but we'll find out. Oh, I took it all with me. Okay, this graph is discontinuous for every x value not in the domain. Okay, it is also discontinuous at x equals 0 and x equals 2. Because let's face it, out at -10 is a discontinuity. Is that the one I'm most concerned about? Not really, to be honest with you. I think we all know that at 100 this has a discontinuity because it just stops, right? Why x equals 0 and y equals 2? Well, at x equals 0, do you agree if I were to fill that in, it would take care of that problem? If I were to just fill in that little hole at x equals 0, 0 there, would it then be continuous for that portion of the graph? It would. Okay. What if I fill in the hole up there at 2, 4? Does that get rid of the discontinuity? At 2, no, there's still a big jump there, isn't there? There's still a big gap. Okay, so one of them is removable, or again, if you want to say it's a hole, that's fine. And then the other one is a jump discontinuity because there's a gap in the y values there. Okay. No, I'm just going to monkey with it. Oh, I have them all grouped. Oh, well. Does that really change my answer? Is this graph still discontinuous for every value? Okay, does it change my domain and range? Changes my domain. What I'm saying is, does it change this stuff that's typed up here? Is this still discontinuous for every value not in the domain? True, but now we have more values that are not in the domain, right? Is there still a removable discontinuity at 0? Is there still a jump discontinuity at 2? So did these discontinuities move by what I just moved there, that little segment? Not really. Did the domain change? Yeah, but I took care of that by answering this up here this way. All that weren't in the domain are discontinuities. Okay? And I'll have to make sure not to save this, so that goes back to where it was. Okay. Any questions? Specific or otherwise?